2000?
Sure. Yeah.
The year?
We're very pleased to have David Huse, who's going to tell us about spin glasses.
Okay, so so this is some work that just came up in the past few months, thanks to so Alan Middleton is at Syracuse, and Creighton Thomas was his PhD student, who's now at Texas A&M, and they did some very nice numerics exploring two-dimensional Ising spin glasses, and I think allowed us to find something new there in the understanding of this very old problem. Okay, so unlike my seminar 2 weeks ago, here we're going to assume equilibrium statistical mechanics. So we're talking about equilibrium at a given temperature, and classical. So it's classical equilibrium statistical mechanics. So it's just the standard Edwards-Anderson spin glass Hamiltonian, which is here. So here's the Hamiltonian, a 2D lattice, short-range interactions, quenched random couplings, and Ising spins plus or minus 1. So the standard Edwards-Anderson spin glass. Now there's two things to say. One is if it's a planar graph, which is a particular type of 2D lattice, then you can apply the technology initially developed by Onsager and many others. And so you can find the partition function or whatever in polynomial time. And that's the technology which Alan has been pushing on a lot recently, and they've exploited this. Okay, so we're going to do, they have nice results for many samples of size 512 by 512 sites on a square lattice with periodic and antiperiodic boundary conditions. And it's getting up to these kinds of numbers, which opened up some new physics which hadn't really been thought about before. And that's what I'm going to try to tell you about today. Okay, so Ising spin glasses in plural. So we have quenched random IID couplings, Jij, and we're going to really look at two models. The Gaussian model, where P of j is a Gaussian, so mean 0, variance 1, Gaussian. So here the couplings are real numbers which are continuously distributed, positive, negative, and so that's what makes it a spin glass. And then we're also going to consider the plus minus j model, which is where P of j, well, the simplest way to do it is to just draw it. P of j is just minus 1 or plus 1, with each with probability half and half. Okay, so here the energies are integers, and here the energies are real numbers. Okay, and so these are in some sense very different models, and they're in some senses in different universality classes, and in another sense in the same universality class. And that's what today's story is about, and how that happens. Okay, what was I going to say? Well, I think that's enough for now. Okay, right. Now we're talking about two dimensions. People who know about spin glasses know that you don't have a spin glass ordered phase at non-zero temperature in 2 dimensions. The lower critical dimension for spin glasses is apparent for Ising spin glasses. It's certainly above 2. It looks like it's below 3. It's somewhere between 2 and 3. So 3-dimensional spin glasses do have a transition into a spin glass phase at a non-zero temperature, 3-dimensional, but 2-dimensional don't. Okay? So we're talking about 2D, which means Tc equals 0. And so we're going to be talking about, when I say universality, we're going to be talking about the low temperature behavior. So we're going to look at low temperature, where the correlation length is bigger than or of order the size of the system, right? So in the infinite two-dimensional spin glass, the correlation length goes to infinity as t goes to 0 with a power law. And we've actually learned now from what I'm going to tell you today that these two models both go with power laws but different exponents, and we understand why the difference now. And if that correlation length is larger than your system, what you're looking at is really a glassy system. It's got order all the way across the system, and that's the regime we're interested in. So it's the low temperature glassy regime where there are correlations on the size of the scale of the system. But of course, the correlation length really only goes to infinity at 0 temperature. So it's all about finite size effects. But also, we believe we have a good understanding of the behavior of the infinite system that we've developed. Okay, so we have two models. This is the simpler one, the Gaussian one. And so I'm going to talk about that one first. It's simpler, but it has actually a surprisingly rich story itself. And then I will tell you how the plus minus j fits part of this, has part of the plus minus j model is universal in the sense that it's doing the same thing as the Gaussian, and then part of it is non-universal and it's doing something different, and how that all plays out. Okay, so if we take the Gaussian model, these couplings are real numbers, and if we take a finite system, say with periodic boundary conditions, there will be a unique ground state up to a global spin flip. So there will be some spin pattern which minimizes this Hamiltonian on a finite-sized system. And of course, if you flip every single spin, you get exactly the same energy because this Hamiltonian is invariant under a global spin flip. So there'll be two degenerate ground states. And then the lowest lying excited state will be at some non-zero energy with probability 1 because we're talking about real numbers, right? And they don't add up to 0, except in rare instances. Okay, so we have two ground states. Okay, so now if we take a system, so we take our system. So there's two ground states. And it's some pattern. The ground state is some random pattern of these spins. It'll just look completely random, but it's dictated by the couplings. So the specific couplings you have in the specific sample dictates the specific pattern of the spins in the ground state. But I'm going to call that pattern, so when I say up in quotes, what I mean is one of those two patterns, right? Which are degenerate, and then down in quotes. So these are the two ground states. Of course, in terms of the original spins, this is a random looking spin pattern, and this is the opposite one, where you just flipped every spin. Okay, so we have two ground states. Okay, so that's simple. And then what about the low-lying excitations? Okay, so what I'm going to develop now, and what I'm doing today, is the droplet theory. And basically what I'm doing today is telling you some additional ingredients of the droplet theory that Daniel Fisher and I did not work out back in the 80s, that we just recently, or I just, me and Alan together found just recently, inspired by his numerics. Okay, and that's really what today's story is adding, an additional little chapter on the end of the work Daniel and I did 25 years ago. Okay. Okay, so how does the droplet theory go? So we want to ask, what are the low-lying excitations of this system, and what are the low-lying excitations of this system on large length scales? Right, so that's what we want to ask. And so the droplet, so here's, say, we have the system in the up ground state, up in quotes, ground state. And then we want to go to this place here, and we want to find the lowest lying excitation on length scale L. And so what we're going to do is we're going to flip a domain, which is going to have a fractal surface, and we're going to flip all the spins inside that domain, and it's going to be surrounded by a domain boundary, and it has size of order L. Okay, so we flipped let's say a nice way to define it is we flipped n spins between L squared over 2 and 2L squared, right? So we've got some flexibility in how many spins we flip, right? It's of order L squared, but let's give a factor of 2 freedom on either side, including spin I. And then we find the minimum energy, and later the minimum free energy. So where do you put this? So this is we call it a relative domain wall, because it's a domain wall between these two ground states. And it's just all the bonds that we flipped, right? And the total energy of that domain wall can't be negative, right? Because if it was negative, then it would have been the ground state, right? So it is necessarily non-negative. Okay, and what one finds is, and I'll say a little bit about how we find this. So we find the energy, actually. So the probability of this energy at scale L versus the energy, okay, it can only be positive. It's some distribution. The shape is not important, but it has a characteristic scale L to the theta, where theta is a power law exponent, which tells you how the typical energy of such a droplet scales as I make it bigger. Okay? And in 2D Gaussian model, or really for any continuous probability distribution, it's not important that it's Gaussian. It's just important that it's not just a set of integers, right? For 2D Gaussian, theta is about, and to the precision I need today, I'll just give 1-digit precision. Oh, sorry. The important thing is it's negative, right? It's negative. So the bigger I make this droplet, the lower energy droplet I can find, right? This domain wall, this domain wall, half of the sections of the domain wall have negative energy, half have positive energy. It has a funny shape because it's finding all the low energy places to go, which are negative, right? But it can't be all negative, because if it was all negative, then it would just flip and that would be the new ground state, right? So it's an interesting little optimization. It's really an optimization problem on top of an optimization problem, right? Because we did one optimization problem to find the ground state, and now we're doing another optimization on top of the ground state. Right? So it's sort of an interesting little mathematical structure. Now, it's important that this exponent is negative, because that means at any non-zero temperature, if I make the droplet big enough, the energy will be of order kT or less, and it will flip spontaneously at equilibrium, and that's why there's no long-range order. So when this exponent changes sign, that's the lower critical dimension. This exponent is believed to be positive in 3 dimensions, where it's about plus 0.2 or something. Yeah, please.
First of all, what is that? What is the theta doing on the axis? I'm confused.
Okay, this is just to tell you the scale. This is a distribution, probability distribution. Integral is 1. Its width is L to the theta. So the typical energy, or the mean energy of such a droplet, is L to the theta.
What's the average?
It could be the average, yeah. It could be the average, yeah.
Okay.
Yeah, it's the average.
So
So this is some probability distribution which has some presumably universal shape, and its scale on this axis scales this way with the size of the droplet.
Now, and then the second question I have is, how do you know that number is negative?
Okay, that I'm going to get to.
Okay.
Okay, so let me just say one more.
Important thing, right?
Yeah, you're right. No, that's again, that's this polynomial-time algorithms. So it's numerics.
What are you minimizing? You're minimizing with respect to the shape of this?
Yeah, so I can put this, I can pick the droplet of any shape, and let's say I just put 2 constraints on it. One, it's of size of order L, which we could say this way, and it's at a particular location, right? Because Because, of course, there are places in this sample where I can make this droplet at arbitrarily low energy. So if I just let it move around, it's going to find something arbitrarily close to 0. So you need to hold it at one location. So I'm giving it full freedom on length scale L only. Right? It can't move over by more than length scale L, and it can't get big.
But it could be as long as it wants as well.
Yeah, and in fact, so the domain wall is fractal with a length going as L to the f. We call that exponent, which is L. And that exponent is about approximately 1.3, again, to, I'm only going to quote exponents to this digit. Of course, the people doing the numerics think they know more, but I like to remain a little skeptical about the last digit that they report.
So basically you constrain the volume, enclosed volume to be where L squared, and the length is just
whatever it chooses. Yes, exactly. And this is what it chooses. Okay. Now, this isn't exactly what we do. What we do, or what is done traditionally, and what Alan and Creighton do. So the numeric. So this comes, this comes from numerics. It's an old idea. These ideas go back, to the early 80s with Bill McMillan and Bray and Moore and Daniel Fisher and me. Okay, so in the numerics, you take a system with periodic boundary conditions. And I'll put it in quotes, periodic boundary conditions. So we take a sample with periodic boundary conditions, and we find the ground state, and let me just call it up. Find one ground state, and we find its energy or its free energy. And now we take the same sample, meaning the same JIJs, but what we do is we flip the sign of the JIJs along one row. So just this set of bonds like this, which are wrapping around the periodic boundary conditions down to here, we change these guys, Jij prime equals minus Jij. So what we've done is we've forced in a domain wall relative to this. Okay? And now the domain wall isn't going to want to sit here. It's going to go and sit wherever its lowest energy is. And so what's going to happen is you're going to get a domain wall, sort of fractal domain wall going around like this, and you're going to have up down here and down here, and then the down matches to the up perfectly across this boundary because I've flipped all the j's. Right? So this is what you do, is you don't do what I was saying here. This is what Daniel and I said. To see here, this is a nice formulation because it tells you what are we talking about in the infinite system, right? But of course, the numerics you do in a finite size system. And so what you do is you force in a piece of domain wall and you look at its energy and its geometry, right? And you get these results, okay? And what we're assuming in saying this and these exponents are the same as the exponents we get here is that this piece of domain wall that I've forced in by this construction, relative domain wall here, has the same properties as a domain wall I would force in by this construction. And this construction isn't that different, right? It's saying I force, right? Here again, I forced in a domain wall. Instead of wrapping around a torus, it has to wrap around a point and be a certain size, but it's not that different a construction, right? And so this you can do good numerics on. So the polynomial algorithms, planar graph, it's okay to have a torus, right? So I guess it's not strictly a planar graph because it's a torus, but they can deal with that and do this up onto this size scale, 512 by 512, and therefore get pretty good data for power law exponents. Yeah.
So the probability distribution is spatially averaged.
Yeah, this would be average over all points in an infinite system, or maybe average over all realizations of the disorder, one or the other.
But it's average, and so in that sense, it's important.
And this you do many samples.
But also the fact that the domain wall is spanning the whole sample, somehow it's averaging spatially.
Yeah. So you do this, and you look at the probability distribution of the energy and the mean length of the domain wall.
It's not clear. If you look at the nucleon state, there's a changed bonds over there.
Yeah, there's one thing I forgot to say here, but finish your question.
Presumably, no reason why that energy has to be higher than it was
Yeah,
before.
right. This is exactly what I forgot to say. Of course, this is just as equally likely a sample as this. So one of these will be lower energy and the other higher energy. And so of the two, let's call the lower energy one periodic, and then call the higher energy one anti-periodic boundary conditions. Right. But if you make a sample and then do this, you're equally likely to get a lower energy than a higher energy. And that's why the domain wall, that's why I like to call it a relative domain wall. It's a relative domain wall between two states, right? And yeah. So we can, just by construction, have this always be positive just by choosing our labels, right? And that again makes it consistent with that. Yeah. Okay, so that's that. Okay, so that's zero temperature, although I alluded to finite temperature a little bit over here. So, but let's now go to non-zero temperature.
Regarding the finite temperature aspects of it, you put in the temperature, then you have entropy.
Yeah, that's what I'm doing now.
Oh, okay.
I'm about to do that, okay? Okay, so we want to go to low temperature, but positive, okay? And what's going to happen now is, okay, so if it's very low temperature, first approximation is, we just turn on the temperature, and what will happen is, so the temperature is, so when I say low temperature, I mean temperature's low compared to the droplet energies. And so what will happen is, in this full probability distribution, these droplets, which are down here at energies of order t, these are what's called the thermally active droplets, which just means they flip at equilibrium, right? And they're going to give, entropy, one of those that flips at equilibrium is going to have roughly log 2 of entropy if its energy is small, less if its entropy is of order t. So we're going to get entropy, okay? Okay, so now, right, of course, right, so the energy of the droplet, so let me now relabel this. So the droplet free energy is, and I'll call that delta F, right? And that's the free energy difference between the state without the droplet there and the state with the droplet there. And that's equal to delta E minus T delta S, right? Where this is the change in energy and this is the change in entropy, right? And the change in energy has this probability distribution. We've already talked about that. How big is the change in entropy? Okay. And now, why does the entropy change when I put the droplet in? Okay. And so why that happens is, let me just draw. So here's a piece of domain wall, right? And say let's say, let me back up a little bit. Okay. So we're in the ground state, and here's a spin here, which happens to be up, plus sign, and there's four couplings coming into it from its neighbors, which are in a certain state. Okay. And occasionally, one of these spins, these four energies holding that spin up, add up to a number that's between 0 and the temperature. It's of order the temperature or less. And that's a flippable spin. So this is if sum on neighbors j, jij, sj, absolute value is less than or of order t, this is an active spin, right? And it has entropy, so it contributes to the entropy. So at low temperatures, and this happens with, so this is you know, so the density of these is proportional to t, right? The typical energy to flip a spin is of order 1 if I have a Gaussian with variance 1, and so the fraction of the spins which are going to be active are going to be proportional to t. And occasionally you'll have a pair or a bigger cluster that's also active, but most of the entropy is single spins or very small clusters, okay? So that spin is now active, right? And typically, you know, what it means is, you know, there's 2 bonds that are happy and are holding it up, and then there's 2 bonds which are unhappy and are trying to push it down, but they're weaker than the other 2, okay? But now I flip the droplet and say this was a frustrated bond here, right? And the droplet domain wall likes to go through the frustrated bonds because that's how it gets low energies. And so let's say the domain wall goes through like this. So here's the domain wall of the droplet. Okay? So now this bond that used to be frustrated is now happy, and now this spin is held up very strongly with an energy of order 1, and it's no longer active, and we lost its entropy. Right? And so that's how the ground state can have higher entropy than the excited state. Okay? But of course it could be the other way around, that I had a spin which wasn't active, and when the domain wall came by right next to it and flipped one of its bonds, it became active. Okay?
But what about entropy of larger droplets inside of the domain?
Yeah.
Since they all
That happens as well. Right? It doesn't, like I say, the active, so here I'm just talking about an active spin, right? But it could have been an active cluster, and the domain wall came through and changed the energy of the cluster.
But since theta is negative, wouldn't those be the predominant effect?
No, because theta is it's negative, but it's bigger than -2, right? So the density of active droplets at scale L is T over L to the theta. So that's the fraction of this distribution that's active, right? Because the distribution is of width L to the theta, and only of order width T is active, right? So this is the fraction that's active, but the density of droplets is 1 over L squared, right? Because I only define a droplet every cell of size L squared, right? So this is the total density of active droplets here, right? And so it's dominated by the smallest scales.
I'm sorry, what did you mean?
Because if I move this site I over by a distance less than L, I'm just going to get the same droplet again, right?
But maybe there's lots of different ways of drawing droplets.
Yeah, okay. That's possible, but we're assuming it isn't. Yeah.
I didn't know.
Right, you know, this is an optimal droplet here, and there'll be a large number of sites I inside of for which exactly the same droplet is the optimum, right? And it's only when I move over a distance of order L that we expect you would get a different optimum. And so that's why the number of independent droplets on scale L, we believe they are of density 1 over L squared. But this is an assumption of the droplet theory, and you know, possibly could go wrong. But well, anyways, I think we can just leave it there. Yeah.
You said something about entropy at 0 temperature. I don't know what you meant. But
Well, I didn't mean to. If I did, that was an accident. Well, actually, no. When I get to the plus minus J model, for the plus minus J model, yes, we have entropy at 0 temperature. But right now, I shouldn't have said that. So that was either a slip of my tongue or of your ear. Okay, so how much entropy are we talking about? So the fraction of the droplets. So we have this domain wall, and it's of this length, right? And the number of spins next to it is this number. And the fraction of them that are active is of order t, right? So we have S, delta S, well, S, well, let me just, right, so we have order T, L to the df active small droplets, which many are single spins, touching the wall of the droplet, right? So this is a big droplet, and then we're asking how many small droplets on its wall are active. And it's this number. And this number is going to be, there's this many in the ground state, and there's this many in the excited state, but there's going to be shot noise. There's just going to be counting noise. So we expect delta S is of order square root of that number, right? We just have n random events, and then we have n random events again. The difference in the number is going to be square root of n. So that's just counting statistics. And so this goes as, so this goes as t to the half, L to an exponent that's about 0.65, which is half of that. And so we have delta E is going as L to the minus 0.3, and T delta S is going as T to the 3/2 L to the plus 0.65. Okay? These numbers being approximate values of those exponents. And one thing you can observe here is as you vary the size of the droplet, we're going to cross over from a regime where this is bigger than this at small l or small t to a regime where this is bigger than this at large L or large t. So there's a crossover from energy dominates at low t, and in particular at L less than some crossover scale, which we call Lx of t. Actually, I forgot to mention, our paper was just posted on the archive yesterday. So it's on the paper's on the archive as of yesterday. Okay. So there's this regime. So this is the basically energy dominated regime. And then entropy dominates for larger length scales, L bigger than that, so there's, right, actually maybe we should say this. Entropy dominates in this regime, and this is the regime that is called chaotic. So now we're bringing in chaos. So this has been called chaotic because what happens is this entropy difference could be of either sign, and so the free energy of the droplet, a given droplet, which has a positive energy, say at 0 temperature, or a positive energy at some temperature, when we raise the temperature, the free energy of the droplet could change sign, and so this, which used to be an excited state, becomes the ground state, and what used to be the ground state becomes the excited state. So the pattern of spin ordering changes as you change the temperature. And at large scales, it changes very rapidly, right? Because at very large scales, this number, L to the plus 2/3, is much bigger than this. And so these droplets, which are momentarily the droplets with the lowest free energy, but have positive free energy, they very quickly flip. And they flip on smaller, and the more you change the temperature, the shorter length scale they flip on. Okay, and that's why, and this is called temperature chaos. You change the temperature, the spin pattern changes. Okay, and a consequence of that, let me just go on. Yeah, okay, just one point is when you put together these exponents, you find Lx of t goes with some power, which I can write the formula, but roughly speaking, just putting in the numbers, it's an exponent of about 0.16. You can also do the formula, write down the formulas, but so this length scale diverges as the temperature goes to 0, where it crosses over from energy dominated to entropy dominated. And a consequence of this, just a second, is if you look at the correlation function, so if you look at the spin glass correlation function, so S of 0, S at position 0, S at position R, take the thermal average of the spin-spin correlation function, Okay, so in a spin glass ordered phase, this could be of either sign, right, because they might be antiferromagnetically or ferromagnetically correlated. So then what you do is you square it and then average over the disorder or average over pairs of spins with distance r. So this is the Edwards-Anderson correlation function, which detects spin glass order. And this is thought to decay, well, this decays exponentially with some spin glass correlation length c of t. And c of t, right, so there's another little bit of the story I have to tell. So that even when we get into this regime here, still delta f goes as L to the theta with the same theta as far as we can tell. And in here, delta E goes as T delta S, absolute value. They're pretty much equal and opposite, and they go still as T to the 3/2 L to the df over 2. So the idea is once you get into this chaotic regime, this is still a good estimate of the entropy of the droplet. The energy of the droplet is pretty much equal and opposite, and the free energy is just a tiny residue left by an almost cancellation of these two, and that cancellation is constantly changing one way or the other, and that's why you get the chaos, right? So this is what appears to occur in this regime. So then you have another scale where, so this correlation length is defined. So C of t is the length where delta f, where the droplet energy at that length scale is of order t. So when, right, the free energy of the droplet is dropping as we go up in length scale, because remember the exponent theta is negative, and eventually at some length scale this becomes of order the temperature, and that's the correlation length, because beyond that scale there's no order. The droplets are just flipping. They're all flipping, and there's no order. Okay? So we get C of t goes as t to the 1 over theta, which is t to an exponent of about minus 3.5. So we have two diverging lengths. So where did I write the other one? Here. So we have two diverging lengths as temperature goes to 0. So this critical phenomenon at 0 temperature has really two diverging lengths in it. One is the correlation length, which is diverging more strongly. And then there's this crossover length. There's an intermediate regime between this length scale and this length scale where you still have spin glass order, but the order is in a different pattern than the ground state. And then there's length scales shorter than this scale, and on shorter than this scale the entropy hasn't come in yet, and the pattern is the same as the ground state. Okay. So this measurement here, this is at temperature T, this is sensitive to that correlation length. But you can also look at this correlation, a two-temperature correlation function like this, S of 0, S of r at temperature T, the same pair of spins at temperature 0. So we can look at the product of the spin-spin correlation function at temperature T with the same pair of spins in the same Hamiltonian at 0 temperature, right? And this is going to decay with this other length scale. So our LX, our crossover length scale. Because beyond that length scale, the spin correlations are in a pattern that's different from the ground state. Okay, so here's two different correlation functions. Temperature, two temperatures, one being 0 temperature. You can also do T1 and T2, and there's a whole scaling with the temperature difference, but that's a different lecture. Okay, because
So if I look at that, the square, or well, no, I wouldn't have the square. I'll look at this spin collection at temperature T, and I vary the temperature. That's gonna be like a random chaotic variable. That's what you mean.
yeah, right. So S0 SR of t before we square it.
Yeah.
This is a random function of t, and the further you go in R, the more rapidly it's going to vary with t. And there's an interesting scaling of that, which you can work out from this. And so that's the story of chaos. Yeah. Now when you do this measurement here, you can do this here and get the free energy of the wall. So F antiperiodic minus F of periodic. So with these algorithms, they can do, right, the partition function at any temperature. And so they get the free energy of this wall as a function of temperature. And that indeed, let me just make a little plot here. It'll start off with some value, and it sort of doesn't change much because this is small compared to this, but then eventually this gets big enough and it starts changing. And it sort of starts changing, they can do a big enough sample so it'll change a few times before it fades away. If you go to too high a temperature, it's gone because the thing doesn't care about the boundary conditions when the correlation length is shorter than the size of the system. But you see it changing. So the chaos shows up in the measurements they can do using these polynomial methods. And the bigger the sample you do, the more crossings you get, and you can do a scaling of that, and that's part of what's in our paper.
David?
Yeah?
I mean, one way also of measuring, so to speak, what's happening is to look at the distance between the ground state and a typical state at a temperature T.
The Hemming distance.
Yes. And
Yeah.
I wonder if that's the kind of how that.
Well, but see, that's going to be zero in the thermodynamic limit. That's going to be zero immediately. But we could say right. So if we did a finite-sized system and we asked that question, presumably this length scale, or we can invert this function to a temperature as a function of L. That would be when that distance just became, as if they were random, right? So on length scales shorter than this length scale, you do that comparison, and they'll be nearby. It won't be as if you pick two random configurations.
I know what you said, it's infinite. If you take
The infinite system, there will, at any temperature, there will be droplets bigger than this that are flipping at random when you change the temperature. So it's going to be, the Hemming distance is going to be,
infinite.
well, it's going to be the same as if you pick two random states.
Yeah, but I guess what you want to ask is you fix your size of your box.
Right.
And you ask per unit volume, so to speak.
Right,
But
something like that,
yeah.
yeah. But I think that's all sort of implicit in this stuff as well. Yeah, right. There's a lot of different ways one could get at this, yes. Let me get to the plus minus j model before we run out of time. Or is there an urgent question?
Yeah. No, I still have this question. Why is theta negative?
Why is theta negative?
Yes. And that theta negative means I don't really have an ordered state. Is that right? I mean,
Yeah.
Is there a Merman-Wagner type argument for why theta should be negative?
Well, if we take a Gaussian distribution, in one dimension, theta is -1.
okay.
Because you take a chain of length L, you find the weakest bond, that's the energy, right? And so theta is -1, okay? So you can see why it would be negative in low enough dimensions, right? And you can imagine it's going to increase with the dimension, right? Right? And now if we put an interface across a system, you're cutting these bonds which are of random sign, and so naively you might think theta goes as, very naively, theta goes as d minus 1 over 2, right? Because you just cut across, and then the bonds are of random sign, so you just add up a d minus, L to the d minus 1 random variables, right? So this is,
That would give you something positive.
so this is well, not in one dimension,
No, not in one dimension.
right?
No, I'm in two.
Now, of course, in one dimension, this would give a half, but in fact, you do something lower than that because you optimize it, right? You haven't just put it at a random location. You put it.
D minus 1 in one dimension.
Right. Would be 0. Would be 0. Sorry. Be 0. Yeah. In one dimension, it would be 0. But of course, it isn't 0 because you don't just put it somewhere and then just see what you got. You optimize it, so it's going to be lower, right? And so theta should be less than d minus 1 over 2, right?
This I understand.
Right. And it starts off with theta of 1 equals -1, and naively it goes up roughly a half per increase in the dimension. So it's sensible that it might still be negative at 2. and it might go positive by 3 if it's going up a little faster than this says, right? But that's just numerology.
But there's no
Nothing.
probabilistic argument that will tell you that this should be the case.
Yeah, well, here's a challenge for you guys.
It is.
Yeah, no, I'm not aware of anything.
Okay,
But the numerics in 2D are very good.
Yeah, and they tell you that this is.
Yeah, it's supposed to be minus 2.28, right, with maybe error of 2 on the last digit, and that's probably reasonably accurate.
So that really is a challenge for us.
Yeah. So it roughly goes as d minus some shift, which depends weakly on d, over 2, right? And in 1 dimension, this shift is 3. And in 2 dimensions, it's a little bit less than 3. And the lower critical dimension is actually below 3. So this shift, when this shift becomes d, that's the lower critical dimension. And one question was, when you go to high dimension, what does this become, right?
Yeah, now in 3 dimensions or
Yeah.
high dimensions.
High dimensions,
Yeah,
right.
what
But this
happens
is, we don't know. This is a challenge. What is this exponent in the limit of high dimensions?
Do you have a guess, or?
Well, it's d minus some small number over 2.
Okay.
But I don't know what that number is.
All right.
And I don't know how to calculate it. You can sort of begin to formulate such calculations in the way Cyrano de Dominicis does these calculations, and you can sort of see this structure, but they've never been able to carry through the calculation. So we don't know. Yeah.
Is there any connection with this model of KPZ optimization where you, in two dimensions, you have this 1/3 and 2/3 exponent?
Not that I'm aware of. At least no direct connection. Of course, that applies to the directed polymer in the random medium, which has a lot of the same glassy scaling as spin glasses. So like the first time temperature chaos was cleanly demonstrated was in that model. But so there's analogies, but nothing direct at all. That 1/3 exponent is like a theta here, and it's like being above the lower critical dimension. But it's
What's theta in 3 dimensions?
It's like plus 0.2, plus 0.3. It's much more uncertain. It appears to be positive. I think there's a good chance that it's correct to say it's positive. Perhaps it's 0 or 0 with logs or something. It's a kind of thing. It certainly looks positive and very small. And of course, you don't have these methods, so.
Yeah. So you can't.
Here we can go up to size 500. In 3 dimensions, you can go up to size 16 or 20 or something like that. And even then, you're not sure you're doing it well, right? So it's a totally different level of confidence and ability to answer the question.
Good, thanks.
Okay. Plus minus J model. Very different, but similar. So the energies are integers, right? And we're interested in temperatures well below the smallest integer, which happens to be 1, okay? So now we do this construction, periodic and antiperiodic, and now in the plus minus J model, we can ask what's the entropy of the periodic and the entropy of the, okay, yeah, let me just back up. So the plus minus, the energies are integers, and in the ground state, in any ground state, a finite fraction, like 2 or 3%, I think, of the spins are flippable at 0 energy cost. And then there's bigger clusters which are flippable. So there is an extensive ground state entropy. So S proportional to L squared. So the entropy is proportional to the area, right? With kind of a small coefficient, but it's a non-zero coefficient, definitely non-zero, okay? Okay, so both of these entropies are proportional to the area, right? But that area entropy, that's just a property of the free energy of the ground state, right? We want to know about the difference. And what's found, again, just numerically, S periodic minus S antiperiodic. And we could call the sample with the higher entropy, therefore the higher probability, periodic. So this is positive. So this thing goes as L. Let me just say, keep L the size of there's some exponent. I put theta sub s, right? So this was theta sub e. I guess it's been erased. Theta sub e. Right? So this is the stiffness exponent for the energy, and then there's a stiffness exponent for the entropy. So this sub s is just entropy. It's this, it's how much does it cost? How much does the domain wall cost in energy? How much does it cost in entropy? Right? And this is a ground state property here, right? Whereas in this model at 0 temperature, there's no entropy, right? So, okay, and this exponent numerically is about a half, plus a half. Let me just emphasize that, plus a half. So there is a difference, much smaller than the full amount. One thing we haven't yet explored, but I think they have the tools to do it numerically, is what is the geometry of this difference, right? So it's not going to be a wall. It's going to be a bunch of places where they're different in their local entropy, local energy density, right? And it's not going to be a sharp wall. It's going to be some structure which is probably going to have some very interesting geometry. It's probably going to be, wide, it's an interesting question which we plan to get into, but we haven't done it yet.
So there's no theta of E defined here, really. That's what you're saying.
There is. Okay, so that's the next thing. Okay, so E periodic minus E, let me do E antiperiodic minus periodic. Okay, so this is 0 with probability about something like 70%, okay? If we have L an even number, right? So if we take an even size system, if you take an odd by odd torus, it can't be 0. But let's just not worry about those details. So if it's an even number, it's something like this. This is a rough number. It's 4 with probability, say something like 29%. These are rough numbers. It's 8 with probability about 1%, and it's 12 extremely rarely, etc. Okay? And these numbers, again, don't quote me on these two. This one I think is roughly right, but it's something like this. These numbers are stable with L. So as you scale up, right? And so that says theta sub E is 0. To a very good precision, right? In that the probability distribution of the energy is now, in fact, let's just draw that. So now, if we make the same plot, the probability distribution of the energy, like I had over here, now it looks like 0, 4, 8, like that. It's discrete, and it has a width of order 1, to the extent it has a width. And it doesn't shrink as you go up in size. Okay? Okay? So now we're ready to talk about the free energy. So delta F goes as delta E minus T delta S. And delta E goes as order 1 minus T L to about 0.5. Okay, so again, it's the same structure, a power of L minus a power of temperature times a bigger power of L, right? But the exponents are different, right? But still, this is a bigger power of L, so you cross over from at low temperature, you have exactly this, except now over here, L sub x of t goes as t to the minus 1 over theta s, which is about t to the minus 2. So it's a different exponent that sets the temperature dependence of this crossover scale. In particular, it's this entropy exponent. And then you have a regime where the entropy dominates and it goes chaotic. Same story. P of E looks like this. Okay, so now I'm going to raise the temperature a little bit, and let's look at P of delta F. But let's say we're still at a length scale a little bit less than this length scale here. So now the entropy is still smaller than 1, but not by a lot. So P of delta F will kind of look like this. Right? Because you've broadened it out by the random entropy, which is random. Right? Right. The entropy difference, the typical value goes with this 1/2, but it has a broad probability distribution, all the way down to 0. It's got a broad probability distribution. So your droplet energy distribution is discrete, which is very different. So this regime, this low temperature energy dominant regime, is very different in the Gaussian model, where you have this probability distribution, and the +-J model, where you have this probability distribution. But as you raise the temperature, this probability distribution gets broader and broader until these overlap, and it starts looking just like this. Right? And so what happens is, for L greater than L sub x of t, P of delta F versus delta F for the droplets looks just the same as it does for the Gaussian, and so you get universal behavior. And so the +-J model matches on to the Gaussian model, and they behave the same. So universal behavior for L sub x of t less than L, well, basically in this regime. So if we look at length scales large compared to this crossover length, probably put 2, we have universal behavior with delta F goes as delta F at the crossover length of t times L, so this is at length scale L, L over L sub crossover to the theta. All right, so the free energy of the droplet is dropping with this universal exponent theta, which is a characteristic of the continuous probability distributions. But by writing it this way, I match it on to whatever it is at the crossover length, right? And this delta F at the crossover length for +-J is of order 1, right? Because it's of order the energy and the entropy at that crossover length, which are of order 1, whereas in the Gaussian model, it already drops from distance 1 down to that. So here it's L sub, it'll cancel this term for the Gaussian model. So this is the general scaling. The two models have different temperature dependencies of this length and different dependencies of delta F on this length, but they have the same dependence on the size of the droplet with the same exponent, right?
So how do you translate that into correlation?
Yeah, right. So now we set the correlation length. So the correlation length, C of t, is set by the condition delta F of C of t equals t, right? So when the typical droplet free energy becomes of order the temperature, that's the length. So actually, let's go over to a new board, and write that out, and you can see you get a different exponent.
So you get a different exponent.
Right. So we have. So let's actually write this out carefully. So for the well, let me just write out the two cases. Okay. So for the Gaussian, delta F at the localization length goes as the localization length to the theta, which is negative, which goes as t, right? And so we get C of t goes as t to the 1 over theta, And theta is negative, and so this is t to the minus about 3.5. Okay? So that's Gaussian. Plus minus j, we have delta f of c goes as the delta f at the crossover length, which is order 1, and then this L over L sub x of t to the theta. So L over L sub x of t to the theta, and this is of order t. So we have to solve that equation. So I put a c there. We have to solve that equation for the correlation length, right? So this is how the free energy at length scales larger than the crossover length behaves of the droplet, and we want to know when it becomes of order t, right? So we put this in. So we have c, and L sub x goes as t to the minus 1 over theta s, and this is all to the theta, and we set this equal to t. And then we can just do this, put 1 over theta here, and then put this over on the other side, and you see c of t goes as t to the 1 over theta like we had here, but then an additional minus 1 over theta s, and so this goes as roughly t to the minus 5.5. So it diverges with a bigger exponent because you get an additional contribution from so that's how that goes. So you get a different exponent
But the distribution.
for the dependence on temperature. So the dependence on temperature is a different exponent, but the dependence on length scale of the free energy of the droplets is the same in the exponent, but different in the prefactors. And the prefactors are where the temperature dependence comes in. Right? So you see, it's kind of intricate, but this seems to be the story, and so we've tested this reasonably well with the numerics, and I think it's, I'm quite confident that we've got this right. So let me just draw a little sketch of this picture here. So we have, right, so here we have Gaussian. So we're going to put on the vertical axis temperature and length scale. And here's 0 temperature. And the Gaussian has S naught equals 0. So it's got a 0 entropy ground state. And over here we got the plus minus J model, which has S naught proportional to the area. So we've got this ground state entropy, extensive ground state entropy here, not here. Okay, and then we go up, and then there's this low T regime where energy dominates, and the two are different. So this is non-universal, right? And then we get up to L sub x of t, or maybe t sub x of L if you're thinking of varying t at fixed L. And that's where right, so this is universal, energy dominates, and that's where we cross over into the chaotic regime, chaotic, glassy regime, where entropy dominates. And once you get into this regime, these two go to, in some sense, the same universality class, because here the couplings coarse-grained out to this length scale. They're continuously distributed even in the plus minus J model because there's so much entropy that the discreteness of the plus minus J model is just forgotten, right? But how you cross over into this regime depends on the model, right? And so this is universal. And then finally you get to the correlation length, and here it becomes disordered. So this is universal, but still strongly correlated. And these are just two crossovers, right? Neither one of these is a phase transition. There's no phase transition at a non-zero temperature, but there's these three regimes, and this universality, which then breaks into two different universality classes in the low temperature regime. And there's a lot more to learn about this guy, as we, you were asking about, I was saying about the geometry of the wall, what do the correlation functions look like. So that's something we're planning on doing, is getting a better understanding of this branch of this low temperature regime, because that's interesting. Let me just state something just for your curiosity, and maybe we can talk about it after the time is up. So here in the so if we take the infinite system, L to infinity, and we look at the specific heat, here the specific heat is dominated at low temperatures by the flippable spins. And it's just C linear in T, very simple. Whereas over here, C goes as T to the 2 over theta S minus 1. So even though there is a gap at low temperatures, so you have the ground state, and there's a gap of 4J to the first excited state, so you would think the specific heat would be activated, but there's so much entropy in this excited state and the ones above it that you end up with a power law specific heat in the limit of 0 temperature. And I can show you that argument, but basically what's happening here, so here the low temperature entropy and specific heat is dominated by the droplets of size 1, of order 1, whereas here at low temperatures we have the droplets with energy 0, which are very active, but they don't contribute to the specific heat because they don't cause any energy fluctuations. And these guys, their energy is 4J, and so they're exponentially small probability of being excited. So you get, in this low temperature regime here, there's no contribution to the specific heat. And at the crossover, the droplets of order 4J start getting enough entropy to flip, and they dominate the specific heat. So it's the specific heat is dominated by this scale in the plus minus J model, whereas it's dominated by the smallest scale in the Gaussian model. And so you get these two different exponents. And then one final last comment. Why are we only seeing this now in 2010? And the reason why is that on this side, in the plus minus J model, this interval here really only opens up and becomes apparent when your samples get of size 100 by 100 or bigger, just because of the way some numbers are. So to see this specific heat with this power law, you can't see it until your sample is bigger than 100 by 100. And you got to have good data at samples bigger than 100 by 100, and we just haven't gotten there till now with the pushing of these algorithms as well as the advancement of the computer hardware. So that's sort of why this is happening now as opposed to many years ago, because it's not really using ideas that are, it's using ideas that were already there when we developed the droplet theory in the 80s. Okay, so I'll pause there.
Thanks very much.